Okay, so today what I'll do is in about 10-15 minutes I'll sort of wind up some things from last time, from yesterday, um, um, and give a slightly better perspective of what I did yesterday, and even correct some slightly the formulae were correct, but I'll correct the interpretations. And then we'll start a new topic, which is focal points of geodesics and then singularities. So the key point here is that we can discuss a killing horizon, or we can discuss a bifurcate killing horizon, and these are not exactly the same thing, because in one case we simply have a single null hypersurface and it has a killing vector which is its null normal. That makes it a killing horizon. In the other case, we have two intersecting null hypersurfaces, and this is the bifurcation surface. Each of these is again a null hypersurface, and again by a theorem I discussed yesterday, there will be a killing vector that points along these null hypersurfaces. So you might think that these are very distinct notions, and right away that is correct. Obviously, when we specify what we want to discuss, either we write that, or we write this, we consider that or this. And also note that, of course, when we consider this, we have in principle different choices of null hypersurfaces and different choices of killing vectors. So it all depends what we want to discuss. Now the key, however, that's not completely true, and what I'll today try to tell you is that if the surface gravity of this thing is non-zero, then this thing becomes this thing automatically. So I defined surface gravity yesterday, and I'll just repeat the definitions. So the first thing, so we are going to discuss both in parallel, but first we'll start with one. And when I get to this point, then I'll complete the theorem I announced here yesterday, that the surface gravity is constant. Yesterday I only proved some part of the theorem, and there's one more little part which will complete. But first, let's just start assuming we have this killing horizon, a single one, and therefore k mu is a function of x times u mu, where this we take to be the affinely parameterized tangent vector, and this is, but this is need not be a killing vector, while this is not affinely parameterized, but it is a killing vector. And then kappa is k mu del mu log mod f. Yesterday I was struggling with where to put the mod, but this is the only place to put the mod. Okay. And by the way, in terminology, this is sometimes, well, this is called the surface gravity, but if we are just doing mathematics of killing horizons, then it can also be called the non-affinity parameter. Because it tells us in what way the geodesic equation for k is not affinely parameterized, because it gives us the right side of that equation. So in fact, k mu del mu k nu is just equal to kappa k nu. Now up to this point, kappa is a function. So this equation implies this equation if u is affinely parameterized, and therefore we have that, and kappa is a function. And then yesterday we proved, and I won't repeat, that first of all kappa squared is minus a half gradient of k, gradient of k. Okay. And Then we proved the theorem which is that kappa squared is constant along orbits of K. And that means in this diagram, going back to this one, so I think N is of course a three-dimensional space because it's a hypersurface with one null and two space-like directions which you can imagine to be a sphere at every point. So pick any point on that and then let me translate along N using the killing vector. Then at the original point, whatever is the value of kappa, it will be the same all along that line, line by line. This doesn't tell me that for one line, so each line, what I'm calling a line is really a geodesic, okay? But this doesn't tell me that for two nearby geodesics, kappa will be the same. It's just the same along a given geodesic. I didn't prove anything more than that last time, and I was in a hurry to end the lecture because of my seminar, so I forgot what I wanted to do next. But the way, the way we proved it though is useful. We proved, let's just quickly summarize it. We said that if W is any vector, any tangent vector to the null hypersurface N, so it could be K, it could be U, it could be, yes?
Regarding the definition of K mu is equal to Fx U.
Yes.
Can you, how we motivated the definition last time?
Oh, because actually we probably said more than we need to. It has to be like this because U is given to be a affinely parameterized tangent vector to a given hypersurface, and K is also a tangent vector to that hypersurface because it's a killing horizon. Killing horizon means that K is a tangent vector. So if I have any two tangent vectors, this relation holds between them. Even if U was not affinely parameterized, as long as K and U and also this W which I'm bringing in here, whatever they are, they can only be one function, scalar function times each other. That's all. So actually we probably said more than we needed to say for that. Exactly. Good. So W mu is any tangent vector to N, then W mu del mu of kappa squared. We showed that this is by simple manipulation, it comes out to be minus W rho del mu K mu and then R sigma rho mu K sigma. Okay. Now, if W mu, if this is a general result which I can use more than once for different W's, but if W is K mu, then RHS is 0 because this becomes K, this is anyway K, and they are anti-symmetrized by these two indices. Okay. Now notice that in this whole discussion I have never said anything about K vanishing anywhere. I have not used that. This distinction I didn't make clear yesterday. I never said any I never used any fact about K vanishing. For all we know, K never vanishes. Okay, and this much is still true, that along orbits of K, the surface gravity is constant. Okay, so we even don't have a bifurcate horizon at this moment. We only have a single killing horizon. However, the second thing we showed yesterday was that K mu, we can actually find this function f in terms of surface gravity, and it comes out to be a constant f0 times e to the kappa alpha. So this is the relation where alpha is such that K is equal to del by del alpha. It's like a coordinate along the orbits of K. So we related this to the, while lambda is the affine parameter, so the vector. I'm putting this when I don't write the component but the full vector. I put this thing below. In the notes it will be boldface, because otherwise you may confuse this with the Kruskal coordinate u, which is also capital. So this is d by d lambda, and we analyzed the relation between them and we found that f of x is this thing.
F not
by kappa. I think I lost that somewhere. Yes. No. F is f naught e to the kappa. Lambda is f naught by kappa. Yeah. F is f naught times this thing. There is no division. Okay. Now notice that just with this relation, which we got only from the relation, so there are two things we went into this relation. One was the fact that k is a function times u, which is quite harmless. Then of course we use the fact that k is a killing vector, and then we allowed the surface gravity to be non-zero. If it's zero, of course, then then k is just u. But for any non-zero, for kappa non-zero, k mu necessarily goes to 0. And depending on the sign of kappa, it will happen either at alpha goes to minus infinity or alpha goes to plus infinity. So actually we've shown that if you take a killing horizon and it has a surface gravity, then that killing vector is going to die out at some point on that horizon. Okay, and a point on that killing horizon is a two surface, and in fact in 4D it can be proved that this is necessarily a two sphere. Okay, so therefore so it goes to 0 at some point along the null hypersurface, and where k mu goes to 0, we get a two surface, which is a two sphere actually. And this is a bifurcation two spheres. The bifurcation surface, because there we can find another null hypersurface which intersects orthogonally, and so we get a bifurcate horizon. So what I want to stress, which I didn't do last time, is that starting with a killing horizon, I get a bifurcate killing horizon for free. It's not something I have to insist on. Okay? As long as its surface gravity is non-zero. It's also interesting that depending on the sign of the surface gravity, so notice that its definition it has a sign because it's kappa on the right hand side, not kappa squared, but the property which we used involved kappa squared. Kappa squared is minus half gradient k. So that's the quantity which actually we proved to be constant along these orbits of the killing vector. And last time people did ask whether therefore it can change sign on branches, or whether it can change on different branches, and we'll see that actually it can, which I didn't realize yesterday. Okay, in fact it's pretty obvious, but yeah, I don't know why I didn't think of that. But first, because we have this, now we can get some new results because of this fact. Vanishing of k makes that equation, which just disappeared from the top of the board, useful now even if w is not k but something else. Okay, because we can recycle that equation to give me p mu del mu of kappa squared, where t is one of the two tangent vectors of the two sphere, the bifurcation surface. And on the right side we'll get something but which ends in k sigma, and on the bifurcation surface k is vanishing. This is new. This is the first time we are using vanishing of k, and we proved the vanishing of k from the fact that surface gravity is not 0. Okay, so now we have the following situation. We have this intersection. Here's my S2. And we've proved that if you start at any point on S2 and go this way, kappa squared is constant. The same proof will also say if you start here and go this way, kappa squared will be constant. Okay, but also if I start at one point on this S2 and go to another point that I do by this tangent vector, then also kappa squared is constant. So it's constant all over this S2, and from each point it's constant over every orbit. Okay, so now it's everywhere constant on the bifurcate horizon. Of course, it need not be constant anywhere else. It's defined specifically. I mean, it's a property of the horizon, so it's constant along the horizon. Okay. Given that formula that says kappa squared is minus half del k, k is defined everywhere, so you can define kappa squared by that elsewhere also, but it's constant along the horizon. So here we get that kappa squared is constant along the bifurcate horizon, which I call B, the whole thing. So it's an additional result. Okay. Now, two small things and then I can move on. One is the sign of k of kappa, and two is the normalization of kappa, and both are important. I mentioned yesterday that in the future kappa will turn out to be related to the temperature, will be the temperature of a black hole. But if you are not sure of the sign, then obviously it can't be the temperature, because temperature is not normally negative. And if you are not sure of the normalization, then also it can't be the temperature, because temperature is an absolute thing and it can't be replaced by twice or 10 times. Okay. So for one, let's take a look again at the Schwarzschild case. So the Kruskal extended Schwarzschild spacetime. There, let's remind ourselves what was k. It was 1 by 4 gm. By the way, this what I am writing now is also nice because it verifies everything we did above in general for a special case, which is after all a very important case. So this is k. We've already written it a few times. What is u? So u is the affinely parameterized null vector along u equals 0. So let's label. We have this. So this is the u axis, this is the v axis, and so u, the vector, points like this. Okay, and v, the vector, points like this. So therefore u is actually d by dv for u equals 0. Now you can understand why I am putting this thing below it. This is a vector field, these are Kruskal coordinates. So if so u goes that way. On the other hand, v is d by du for v equals 0. Okay, so now all we have to do is to verify the relation that kappa is proportional to u on that surface and proportional to v on this surface, and it is, you can see it from there. So on u equals 0, let's work on this surface first, which is that one. Kappa is just the first term because the second term has vanished, and it is proportional to d by dv, which is the vector u. So kappa, sorry, k, I mean, not kappa. K is 1 by 4 gm v times the vector u. So therefore the function f is this. Okay, therefore the surface gravity is k mu del mu log mod f. Now f is this function, so it depends only on v. So this is k, the v component, okay. Then del v of f divided by f, and k v component is 1 by 4 gm times v. It's just whatever multiplies del by del v, and del v of f by f is 1 by 4 gm divided by v by 4 gm. So it's just 1 by v. So at the end of all this, it is 1 by 4 gm. So we've calculated the surface gravity on that axis and found that it's 1 by 4 gm. Okay. Now let's calculate it on the other axis. In that case, I have to first write the relation between k on that other axis. That is that hypersurface, we gave it a name n prime earlier. So it is 1 by 4 gm minus actually times u times the vector field v. Just the reverse of that. Now you might think, aha, that means this function f is negative, but that's not going to change anything because we are actually doing del mu of log mod f, okay, or del mu of f over f. So this sign won't actually matter. But now, if we write the surface gravity, it is k mu, same definition, but it's now going to be ku del u of f upon f mod, del u of f upon f, where the mod is automatic because both will be negative. And this, now ku is minus u by 4 gm. Is the second term in the definition of k. That's the minus which is important. And del u f by f is just 1 by u. So we finally find that the surface gravity is minus 1 by 4 gm on the other branch of the bifurcate horizon. So actually it is here 1 by 4 gm and also here and it is here minus 1 by 4 gm and also the whole line. Okay. Now let's see if this makes any sort of physical sense. Well, first of all, it's positive and 1 by 4 gm on this thing. So this part is the future event horizon for the observer who is sitting here. This is region 1. So it's good that it's positive because eventually, just assuming we will be able to identify surface gravity with a temperature of a black hole which radiates, then that temperature is positive and physically sensible. Okay. Let's ask what it means over here for this temperature to be negative. This is the temperature of the white hole or past event horizon. The fact that the white hole has negative temperature means that the world outside will radiate into it, but it can't radiate out. Okay, so this is also correct. You might be puzzled if you live in region 4, because here apparently the black hole has a negative temperature, because this is still minus a negative surface gravity, and the white hole has a positive surface gravity. What sense does that make? Well, the way we understand that is that, remember, the killing vector which started life here was going this way, but here the killing vector is going backward in time. Okay, and that's really why. So if I want to understand, if I want to take the democratic view that an observer in region 4 has every right, just as region 1, to see the same setup, then of course I should give this observer a future directed time and not past directed time. That will require me to change the sign of k. As soon as I change the sign of k, the sign of kappa will change, and that person will get a positive temperature for their black hole and a negative temperature for their white hole. So everything is fitting. Good. Okay, so that closes the issue of sign. And the last issue is the normalization. And here we encounter the usual problem this killing vector, which defines the killing horizon, is null on the killing horizon. So if k is a killing vector, then if I scale it to a times k, it's still a killing vector for a constant a. Doesn't change anything. Moreover, k being null on the hypersurface, of course, is preserved by scaling it. So it looks like there isn't really anything I can do on the horizon to decide how big is k, or how k is scaled or normalized. And if I can't do that, then I can't also normalize the surface gravity. But k is defined everywhere, so the solution is go to space like infinity, I0, which is far on the right of region 1. It's here. Actually, if I did the Penrose diagram, then there would be something like this, right? So far, we have not bothered to use the Penrose diagram specifically, but we can. This is I0. So I somewhere here, let's say. And here, of course, as you know, the killing vector is time-like and points in the future. And so here I normalize, so go to I0, 2 meaning near, and normalize the killing vector there, so that k dot k is -1. This is the standard normalization for a time-like vector. And once I have done that, since it's a continuous function, it's normalized everywhere. And now I have a unique normalization for the surface gravity, and therefore I have a unique value. And that's why 1/4 GM is correct. So actually, we should be verifying that k squared in the Kruskal coordinates is actually -1 at space like infinity, and I'm pretty sure that's an easy calculation. You just have to use the Kruskal metric for that. Although for a moment I'm having a slight panic because the Kruskal metric has GM cubed in it. Am I not wrong? Am I wrong?
Yeah, there is a GM cube.
Where is a GM cube?
32 GM cube by R.
Well, I'm sure it works out. We just have to do it. There's that R also, right? And that eventually is going to go to infinity. So somehow it will work out, and it's an exercise. Okay, good. So with that, we move gears into something which I'll start today, but we'll do it more seriously from next time. And that is the study of focal points. So now there's an interesting thing here, which is that if I wanted, I could have talked about focal points right in the beginning of the course, because it's an elementary concept involving geodesics. The real subtleties are in the same issues when they concern null geodesics. And as you certainly know by now, our intuition for null things is not so good, and they just make everything more difficult. And so we'll have to study focal points separately for time-like and null. So I decided to do them together, one after the other. But we'll first spend some time doing time-like geodesics strictly, and then only we'll move to the null case. Now, even before going to time-like geodesics, we can consider Riemannian geometry again. And here, as you know, the geodesic equation is just xi double dot plus gamma I j k, x dot j, x dot k equals 0, and I can take this parameter to be the invariant length along the geodesic. And very good. And now let's just think of a manifold, simple manifold like an S2. This is just a geometry exercise. And let's consider geodesics that all come out from the North Pole and go down. So let's in particular consider this one as well as this one. These are all great circles, or half of a great circle, and they are lines of longitude. Now we notice that from this point there is a 360-degree set of directions, and these can go out all over those directions, and they diverge from each other, they separate more and more, but then they reach a maximum separation here, and then they come back to together and meet each other again. So this is our first example of a focal point. This is a sort of informal discussion on focal points, and then I'll write some equations which will make the definition more rigorous. So it's basically where two geodesics meet. So actually, not just that, where two geodesics starting from a common point meet again. Just two geodesics meeting is not a big deal. At the North Pole, infinitely many geodesics meet, but when they start from a common point and then meet again, then it's called a focal point. So we can call this P and this point P prime, and the geodesics have met. Now, what's the bad thing about geodesics meeting? You could say, so what? And there's nothing obviously bad until you realize the following. Let's try to take this one and just continue it up to here. Okay? So the line I'm considering now is P to Q, going from north to south pole and continuing back up to here. Now, until this focal point, anywhere here, geodesic was minimizing distance because we are in Riemannian geometry. But clearly this path is not minimizing the distance from P to Q, because the shorter distance from P to Q is just that. Okay? So we see in an example that after the focal point, extending a geodesic does not minimize length. So you have to, once there is a focal point, you need to do something different. Now, let's try to see in a more general, this was a nice simple example based on a sphere. Let's try to see a more generic situation. And in that generic situation, I'll take, let's say, a point P here and a point P prime here. I have in mind some arbitrary Riemannian manifold now, and I'll take one geodesic and another such that they have a focal point. In the literature, these are also called conjugate points because there's a pair of such points, but there are subtle differences according to who uses the terms. I'll mostly call it focal point, but we'll see in the definitions what to call them. So they meet like this, but now I'm going to assume something else. I'm going to assume that they meet with a very small separation. So they are very close by. The reason is that you could get misleading conclusions if, for example, the manifold has some awful thing hidden in the middle, like let's say there's a black hole here, We don't want to consider one geodesic going this way around the black hole and one going that way. That would be that would be, the whole discussion would be disturbed by something very significant, a singularity or something in the middle. But here it's only the geometry of the manifold which is affecting what is a geodesic. So now with this, so I'm going to rub this out, but we understand small separation here. So now let's say that I naively continue this geodesic like that, and this is Q. So it's an infinitesimal version of what we did above. How do we see that it no longer minimizes the length? The way to see it, it's actually a very ingenious argument and seems to have originated with Penrose. It's in his book, and then it's used by many people, is that I can actually, I noticed that there's a kink over here. That means, okay, first of all, these are both geodesics, they both minimize the distance up to P prime. So the invariant distance this way and this way are the same. Okay, so I can as well take this path from P to P prime to Q and replace it by P to P prime over this and then to Q. It has the same length. Okay, but looking at this lower path, I see that I can reduce its length by smoothing the kink. And simply what I do is I join it like this. What you see is that locally this kink makes a sort of two sides of a triangle, and a single side of the triangle is going to have less length than the sum of the other two sides. Okay, and we are doing this in a small enough region. So there are two, so therefore the way I like to say it is that to see this, that after a focal point extending a geodesic does not minimize length, we carry out two operations. One is replace gamma by gamma prime. These are the geodesics only between P and P prime. Okay, so I call this switching. And two, replace gamma prime plus whatever is this new thing. This is the segment P prime 2 by, I don't know, delta, which is this dotted one. This is gamma double prime. Okay, and this smooths out the kink and it will have shorter length. Okay, and therefore there is always a procedure to reduce the length from P to Q compared with what you would get if you followed a geodesic once the focal point has been crossed. Okay. Now, there's an interesting generalization which is actually will turn out to be relevant. Supposing, so here's a generalization. Let's call this angle alpha. It's a small angle where these two different nearby geodesics focus again. So the generalization is, let gamma still be a geodesic, but in my diagram, gamma prime is a non-geodesic. Okay, but it is approximately a geodesic in the following sense. So first of all, if gamma prime is not a geodesic, then this isn't even a case of focusing. You can't say focal point because one of these two things is not a geodesic. Now, when something is not a geodesic, it obviously fails to satisfy the geodesic equation. So x double dot I plus gamma I j k x dot j x dot k for the second thing is just not zero. If it's not zero, okay, Yeah. So since this is a small deviation from this by an amount alpha, this non-zero number will be of order alpha in general. Good. Now, I forgot to say something first. Sorry. This is a generalization, but before I discuss the generalization, I didn't say something important. How much do we save by going to delta compared with this kink? We reduce the length, but what is the order of saving in length as a function of this infinitesimal parameter alpha? And here we use the fact that a geodesic, since it minimizes length in Riemannian geometry, it is stationary under first order perturbation. Okay, so the saving in delta will be of second order in alpha. So delta is a shorter path to order alpha squared. That means there's no to first order in alpha. There's no gain by going from this kink thing to this thing, because these segments are all geodesic, and if I deform them to first order in alpha, they're stationary because they're geodesic. So this is an important point, that the deviation, the improvement in length by switching to delta is of order alpha squared, not alpha. Now we come to this generalization. So here the idea is that the non-geodesic fails to satisfy this equation, and now if I can still try to shorten the length, but when I switch to the dotted line, I'll have two effects. So when we switch, there are two effects. One is shortening that would take place by order alpha squared, and the other comes from the non-geodesic nature of gamma prime. And this one actually is going to be a lengthening, because this curve is actually this non-geodesic curve is originally longer than that one, and for the same reasoning it's longer by alpha squared. So there are two competing effects, and when there are competing effects, you can't say which one wins without knowing details. But you could do something clever. You could take the non-geodesic to violate the geodesic equation only in order alpha squared. Then the lengthening would be an order alpha cubed effect. And now it would be much smaller than the shortening. So still you gain something by switching to the dotted line. Okay. So you can think this through, or if you want to read about it, Witten has a very nice explanation in his light rays lecture notes. So the idea is that a focal point can be generalized to something which is which looks like a focal point, but between a geodesic and a non-geodesic. But your non-geodesic is carefully chosen to be non-geodesic to be geodesic to one higher order than necessary, and then its non-geodesic behavior starts at the next order, alpha squared. Okay. There's another direction to generalize both the ideas, the focal point as well as this shortening between a geodesic and non-geodesic, and that's when I consider, instead of 2 points, I consider a point and a surface. It could be any surface. Now I can ask for a geodesic from the point to the surface. That's The idea here is that I fix my point and I want the path of minimum length which lands anywhere on the surface. It could land here if it would help it to minimize length, but obviously in the diagram it wants to land as close as possible to the nearest point on the surface, and then it will choose the path to minimize the length. That much is clear, and actually it's pretty easy to see. If this is some smooth manifold, it will come and hit at 90 degrees to that manifold, because any other angle it will just increase the length, sort of Pythagoras theorem. Because if it comes here at some angle which is not 90 degrees, then there's a triangle, then there is another path which has 90 degrees, and then I get a triangle, and then I see that finally this was going to be shorter than that. I mean, this is not of course a complete proof, because there could be something in the geometry which tries to favor that one, but at least very close by you can convince yourself, so therefore you can convince yourself that finally the thing which minimizes length will be at 90 degrees by taking a point very nearby to it. Okay, so here we'll say a focal point is when there are two geodesics both orthogonally intersecting the surface and both starting from the same point or ending at the same point. So this is a generalized focal point again, but it's not between P and P prime, it's between P and the surface S. And as far as this approximate geodesic argument goes, it's exactly the same. And again we have a small parameter alpha, which is the separation between neighboring geodesics, and then we get length. We can save some length by switching the path to the one which smooths out a kink. So again, the story would be that if this happens, then there would be a point over here Q for which this path from the surface to P to Q would not be a geodesic. And to find the new path which is shorter, you would start here, go to P, then go to Q for the same length, and then you would short circuit it by switching to a shorter path like that. Okay. Now we have to ask the same question for Lorentzian manifolds. This was fine for Euclidean signature or Riemannian manifolds. And for Lorentzian case, pretty much everything is the same as long as we restrict to time like geodesics. I think we saw last time that space like geodesics don't do anything interesting, but time like geodesics maximize proper time. And therefore, in these kind of constructions, what will happen is that by smoothing a kink, I'll get a path of longer proper time, larger proper time rather than smaller. Now, that's an important difference. Okay. So now this is all sort of nice pictures and words, but we can do better by using a concept that I introduced quite long ago, and that is the concept of a Jacobi field. So let me remind both of us what that is. So let's recall Jacobi field or Jacobi vector. At the time we discussed this, the idea was, supposing I have a geodesic with now always time-like in this discussion. So there's a time-like parameter proper tau which parameterizes it. But then supposing I have a congruence, then I have lots of geodesics filling up all the space transverse to one direction. Okay, a whole bundle. But sometimes it can be convenient to pick out one transverse direction and give it the name small s. Okay, so that a point in this family, which is like a two-dimensional, it's a one-dimensional family of geodesics So it's a two-dimensional space. So a point will be parameterized by a location tau along with, first of all, a value s, which tells me which geodesic I am on, and then a value tau, which tells me where I am on that geodesic. Okay, good. So now, given this, all the points in this space, which is a subspace of the full one, unless I'm working in 1 plus 1D, then it is the full space. The points are labeled as x mu of tau and s. And we know that u mu equals dx mu by d tau at any s is the tangent vector to that particular geodesic. But what is the vector s mu, which is equal to dx mu by ds? You can think of it as a deviation vector, which is a vector based at a particular geodesic, at a particular point on a geodesic, and pointing to the next geodesic, if you like. The important thing though is that this vector doesn't require two different geodesics for me to define it. Okay, I simply have one geodesic x, but I differentiate it with this. I'm not explicitly introducing another geodesic. I'm just differentiating the first one with respect to an infinitesimal motion sideways. I mean, maybe I overstated it. Obviously, if it can move sideways, it will move to another geodesic. But in the sense of calculus, I'm finding its derivative on it. Okay, good. Then what we did last time was to note that because these two vectors, so therefore u, from this it follows that u, the vector, is just del by del tau, and s is del by del small s, and so they commute. The Lie bracket is 0, and we get the equation u mu d mu of s mu is s mu d mu of u mu. Okay, and then this part we gave the name b mu nu, and so we had an equation which says that the parallel transport of this Jacobi vector, so this is the Jacobi vector, parallel transport of it along a geodesic, which is this, is some rotation of it by the matrix B mu nu, which is space-time dependent. And then we actually use that to define things like the expansion, geodesic expansion, and rotation, and the shear, and so on. Okay. And then we derived an important equation called the geodesic deviation equation. And that equation says that del tau squared of s mu, so del tau of course is the same as u mu del mu. So it's an equation for the second derivative of the Jacobi vector along a geodesic, and it took quite some manipulation, but in the end the answer was this is alpha, then this is u mu s nu r alpha beta mu. Actually, this is not the way I want to write it. R alpha mu rho u mu s rho. Simpler to remember also. So it's a second order equation for the Jacobi vector, and it's given in terms of the curvature. and that's not surprising. So it's always nice when the curvature comes in. If you remember, the killing vector lemma actually is not that different from this in some way. It's about a completely different object, and some details are different, but it also is a second derivative of the killing vector given in terms of curvature. And you can each time see that nothing interesting happens to the killing vector, or in this case the Jacobi vector, if the space-time is flat. But as long as there is a curvature, something will happen to it. Okay, good. So that's the Jacobi field. And now we gave a definition of focal point. So in terms of a single geodesic, 2 points P and P prime on a geodesic gamma are called focal points. If there exists a Jacobi field or Jacobi vector S mu all along gamma that vanishes at P and Q and P prime. Now we don't want to right now rule out that it may also vanish somewhere in between, though that would be another focal point. But certainly it should not be zero everywhere. Like you could always take S mu equals 0, then it vanishes and you haven't learned anything, but not everywhere. That's just a little caveat. And now many things become in a way simpler or more elegant, because we are not talking about two geodesics and we are not asking the question that they are separated by some order alpha. In some sense, this definition takes the alpha going to 0 limit of that focusing phenomenon which I drew. That's why it involves derivatives in the direction away from it. Okay. So one of the nice things is that this weird example I gave you, that there could be one geodesic and one non-geodesic focusing effectively in a way that again changes the rule too. I mean that again doesn't minimize length in the Riemannian case. That's encompassed in this definition automatically, because this definition nowhere says there has to be another geodesic that meets the first one. Okay, so anything which will make this Jacobi vector vanish at the beginning and end, I mean any Jacobi vector which vanishes at beginning and end is good enough. And this you can convince yourself that this vanishing at beginning and end will allow for the possibility of one geodesic and one non-geodesic which deviates to second order from being a geodesic, the case that we discussed about. So everything is included here. Okay, and you can also extend this definition to gamma from S to P, where S is a manifold, submanifold. Can be any codimension. Most often it's some hypersurface or dimension, codimension 2 surface. So we discussed how there could be focal points in the intuitive sense by drawing pictures, but instead of that we can now ask for a Jacobi vector to exist on this geodesic from the surface to the point and to vanish on the surface and on the point, at the point. That still we'll call that a focal point. Okay. Okay, now there's an exercise, I'll leave that to you. Maybe I'll add it to, I still have to give that problem set. Maybe I'll add it there. Let me write it down. Show that in a globally hyperbolic spacetime, any geodesic has, okay, maybe there's something I forgot to emphasize. See, geodesic is not defined, at least by me, as the thing which maximizes or minimizes proper time. Geodesic is the thing where the tangent is parallel transported. Okay, so in fact, from that definition, in the original example, if I did go from P to Q like this is a geodesic, it just doesn't minimize the length. And this is a geodesic which does minimize the length. However, this longer one has a property that though it didn't minimize the length finally, but there's a smaller part of it which does minimize the length. That's the exercise. As an initial segment, that maximizes property. So it's sort of making, it's sort of telling us that, well, maybe the geodesic you're looking at doesn't maximize proper time because it had a focal point, but there must be some part of it before it reached a focal point which was doing that job. But it does invoke global hyperbolicity. Okay, and now it's pretty straightforward. Let's remember that we have the Raychaudhuri equation. Again, quite simple for the time-like case. And so theta was defined as half g dot over g, where gij is the spatial metric in synchronous coordinates, where it's orthogonal to the time direction. And it satisfies the equation theta dot is equal to -1. Here I can go back to generic dimensions, no need to be in 4D. Theta squared minus trace sigma squared minus r 0, 0, which in turn, when I use Einstein equations, that part turns into 8 pi g t 0, 0. T hat, if you remember, I'll write the definition. And there's also a cosmological contribution, 2 by d minus 2 lambda, with a plus sign. And this term is positive, therefore with a minus sign it's negative. This term will be negative only if, so first of all, t hat 0, 0 is t 0, 0 minus what factor? I forgot already. Yeah, 1 by d minus 2. So t hat mu nu, I'll write. G mu nu T alpha alpha, the trace. And this being T hat 0, 0 greater than 0 is called the strong energy condition, or the dominant, what is it called? Strong, no? or dominant. I never remember. Yeah, strong. So these are just terminologies, and there are a lot of discussions on which one is more reasonable or which one is more reasonable. But if we just ask for T00 to be positive, that's the weak energy condition. We ask for this to be positive, which is the strong one. But actually neither is weaker or stronger than the other because we don't know the sign of T alpha alpha. If this is positive, one of them is stronger than the other. If it's negative, then it's the other way around. So they are just different energy conditions. But we'll assume this one so that this term is negative. And then we'll also assume that lambda is either not there or it's also negative. Both of which are of course contradicted by experiment. But okay, at the time some of these things were done, it was not known that it's positive. And maybe people are still not sure, but okay. So if that is so, then you, under all these assumptions, then you get the result that theta dot plus 1 by d minus 1 theta squared is greater than 0, sorry, is less than 0, less than equal to 0. And now you can integrate this to get a bound which says that theta inverse, 1 over theta, is greater than or equal to 1 over theta 0 plus 1 over t minus 1 times t, where theta 0 is just theta at t equals 0. And now see what happens. We ask the question, when will theta diverge? And you can see from that equation that it's going to diverge when g goes to 0, the determinant of g. And the determinant of the spatial metric is just one. This again I'm doing a sort of informal discussion, and we'll do a formal one. Determinant of the spatial metric in synchronous coordinates tells me how close two geodesics are, because it's basically the volume of that space-time region. And if that's going to 0, then that's the place where they'll focus. This was Raychaudhuri's criterion for focusing. So what we notice now is, if theta not inverse is negative, then theta inverse goes to 0 at some in the future. So this is negative, but this is positive and increasing linearly with time. So there will be some time when this positive amount cancels this and theta inverse goes to 0, and that's exactly when theta diverges and we have a focal point. So Raychaudhuri's equation actually tells us that there is guaranteed to be a focal point in the future if the initial condition is negative, and conversely, if the initial condition is positive, then there is guaranteed to be a focal point in the past. The same argument, just run it the other way. And then that means that geodesics, now we are all, by the way, we are always considering orthogonal geodesics. That's built into the fact that there is no rotation term in the Raychaudhuri equation. So that from some hypersurface they go out orthogonally, they are hypersurface orthogonal. So always focus within a time t focal, which is d minus 1 upon mod of theta naught, and depending on the actual sign of theta naught, this time will be in the future or in the past. Just that equation. Just make the right side of that 0 and then you get dy minus 1 over theta naught is the focusing time. Good. And now of course we can write this all in covariant form, and the next step, which will take some time, so I think I won't do it today, is to write the geodesic deviation equation and solve it. Okay, so that will give us a more formal answer for the focusing, and in terms of the Jacobi vector, and then we can check the focusing criterion as we define. This is, I will call this, if you like, informal focusing criterion, that G goes to 0 or expansion goes up, but the more sophisticated version is to define theta in the terms of that Jacobi vector as the is the divergence of the tangent vector to the geodesics, and it's one of the components of that B mu nu matrix which appears in the equation showing that the tangent vector and the Jacobi vector, their Lie bracket is 0. So we'll do that. So just to anticipate what we are going to do, first we'll make the geodesic deviation equation and the condition for focal points a little more formal, and then we'll actually bring in Hawking's theorem, singularity theorem, and it's actually surprisingly short discussion, for the reason that Hawking's main contribution was to add the requirement of a Cauchy hypersurface, which makes the spacetime globally hyperbolic. But again, if that's all that one wants to say, I could say it now in the next 5 minutes and it would be over. But we want to be a little more formal, so we'll write all these things more formally next time. And with that, we would certainly next time finish the discussion of Hawking's singularity theorem, which is the statement as people understand it of Big Bang. Then we will turn to black holes, where the discussion is far more subtle because it involves null geodesics and we have to focus null geodesics. And now we don't have any obvious way to say what reduces or increases the proper time, because the proper time is 0. So life is far more difficult, and that's the one which will take some time. Then we'll apply that to Penrose's singularity theorem, and then we'll talk about the laws of black hole thermodynamics, and by that time it will be sometime in late May, and we'll end the course there. So I would say that today we have embarked on part 4 of the course. If you want to think of it as divided in sections, the first section was basics, mainly geodesics, and null hypersurfaces, the geometry, and then maximally symmetric spacetimes, all basics of geometry. The second one was causality, which had some tough things in it, like this, well, it had domains of dependence and all that, but then it had global hyperbolicity, and then this compactness of space of curves and so on. And then part 3 was black holes, which is finished today essentially. And of course we'll come back to black holes when we discuss all the things after Hawking's singularity theorem. And then part 4 is all this. Okay, so I'll stop here.